In this lesson, we will take a look at how to find the area between two curves. So it does say substitution, but we've already covered substitution in previous lessons. So this is just a rehash of what we did with substitution. We don't really need to do it today. Today's work is going to be mostly calculator, hence why I've got the calculator pulled up to the side here. So very quickly with the substitution, it is the chain rule antiderivative essentially, where you replace that interior function g of x with a u. So this, the only difference really is being definite integrals. So the same rules apply for indefinite integrals, but if we have limits, then to evaluate those, we change the limits to the function values ga and gb. So that's the only slight difference here now that we are evaluating these antiderivatives, getting a numerical answer. We do need to just change those limits of substitution if we choose to do a u substitution. More of what we're going to do today is finding area between curves, and this first property is not something that you necessarily need, but it's something that can speed up your integral process if you recognize it. You kind of need to know what the graph looks like. So if you're doing these by hand and you're not graphing them, you might not recognize functions to be sort of in these patterns. So this, again, is just a little bit of a help, but you kind of need to know something about the function. So what this is basically saying is if we've got a function that's symmetric, then we can do one of two things. So this first example, A, is symmetric over the y-axis, which makes it an even function. And when the function is even, we have the same area to the left and to the right of the y-axis. So this orangish colored area is the same as this light blue area. So instead of taking the entire integral as it says down here, from negative a to a, we can actually just take the integral from 0 to a and then double that. So why would we want to do that? Well, it's a lot easier to take the integral and evaluate it at 0 than it is to evaluate it at, say, like a negative number. And that's because if it's an x function and there's x's in every part, whenever we plug in 0, that part's just going to be 0. So we're essentially just evaluating the upper limit, which can make our problem a lot easier. Similarly, if it is symmetric over the x-axis, or if it's an odd function, then we have the total area here, if these parts are corresponding, will be 0. So this first orange piece and this first blue piece are the same area, just on opposite sides, so they have a net of 0. Same with the second blue piece and the second orange piece, same area, opposite sides of the x-axis, so they have a net area of 0. So the total area is 0, since it's symmetric above and below. Again, these are very special cases, and you have to know something about the function to recognize that it is symmetric. If you're doing this on a calculator, I wouldn't waste a lot of time going through and finding all of this. We can much easier just plug in the function with the given limits and evaluate from there. So then there it is formally. And this is really what we're going to spend the bulk of our time doing today, which is finding the area between two curves. So this blue curve is the upper curve f and the yellow curve, lower curve g. And then we have this blue shaded region between a and b. So this process is not terrible. We just need to either have a calculator and enter it in correctly, or take the difference of two integrals. So if it's a basic function, we can do everything by hand. If it's a little bit more advanced, we'll be going on to the calculator. So they talk us through using Riemann sums. So if you're interested in that, there's some more information elsewhere about what we're getting to, but essentially it's the same thing that we had when we just use a Riemann sum to find the area from a curve to the x-axis. So if you kind of just draw a bigger line through the x-axis, the boxes between the blue curve and the x-axis would be positive areas, a positive Riemann sum, and then the area of the boxes between the yellow curve and the x-axis, since it's below the x-axis, those would be negative areas. And when we find the total area, we take the difference of those two areas. So the positive area minus the negative area to get a net positive answer. Unlike the symmetry up here where we have a total of 0 area. Whenever we have two curves, the area between those two curves is always going to be positive. We're going to take a net area between those two curves, which is always a positive number. So any positive number minus a negative number. And that's what builds us into this formula. So if f and g are both continuous curves, that's been a staple throughout all of this, with f greater than or equal to x throughout, so f is the top function, g is the bottom function, the area of the region between the two curves, f and g, is the integral of f minus g. So the positive area minus any negative area, or the top function minus the bottom function. That's going to give us that blue shaded region, that area between two curves. We can do this all together in the calculator, or if we're doing it by hand, it is generally going to work out that the functions will either go together or it'll just be a bigger sort of compound function, and we can take the smaller pieces with their antiderivatives. Here's some more with the f of c sub k and the delta x sort of ideas. We're not going to dive too deep into that. Here's an example with some functions that are a little bit more involved than we're going to look at right now. So we'll skip through that one. We're going to get down to this. So this still does show this delta x in the rectangle there, but we're going to do it solely with an integral. So what we want to do, we need to get all of the information that goes into this equation. So we need our lower and upper limits, a and b. We need to know which function's on top, so that's going to be our f of x, and then which function's on bottom, that's going to be our g of x. And all of that stuff is pretty laid out for us here. If we look at the two functions, if they don't tell us that we're starting here and ending here, then our limits of integration are the intersections of those two functions. And if we look on the picture they've given us here, the graph shows the line and the parabola intersecting at two places. First location is here, second location is here. So if they do not give us a bounds, a left and a right bounds, the bounds come from the intersection of the functions. So the left point of intersection is negative 1, 1. Okay, so which value do we pick out of that? That's an ordered pair. Which value do we use? Well, we are going to be integrating x, and they've given that to us here with delta x. The equation is set up with dx, so we're going to be using the x coordinate for this. So our left intersection, our lower limit, is going to be that first value, that first x value, negative 1. And then our upper limit, our right-hand intersection, is going to be the second x value of 2. Then we want to set up our integral with the top function. So this does require us to know what the graphs sort of look like, what their relative position is. A lot of the time you'll have a calculator for this, so if you're not sure which function would be on top, you can very quickly graph them and take a look at it. If you don't have a calculator, if there are a little more simple functions like this that you're expected to do the integral by hand, I would suggest either using pre-calc and algebra skills to go through and graph them, XY table, whatever you need to do, but make sure you understand which function is on top. If you don't have the right function on top, you're still going to get an answer. It's just likely going to be the negative of the answer you want. So our answers for these should be positive because it's an area between two curves. So if you do get a negative, what that means is you've had your functions in the wrong order, switch them, and it should give you the same value but positive. So for us from the graphs, it's pretty easy to see that the parabola is on top. So we'll start out with 2 minus x squared. And I'll just go ahead and throw that all in a parenthesis right now, minus the lower function, which is negative x. So if we wanted to do this by hand, we should be able to. The functions do sort of not really go together. There's no like terms, but we can simplify that integrand just a little bit by distributing the negative and dropping some of these parentheses. So we've got 2 minus x squared. That becomes plus x. If that order feels weird to you with the not standard form, go ahead and rearrange it. I'm not going to waste another step doing that though. So the antiderivative of 2 is 2x. The antiderivative of x squared is x cubed over 3, and that is minus. And then the antiderivative of x is x squared over 2. We're going to evaluate that between negative 1 and 2. So if we plug in 2, we'll have 2 times 2 minus 2 cubed over 3 plus 2 squared over 2 minus 2 times negative 1 minus negative 1 cubed over 3 plus negative 1 squared over 2. Okay, so we've got some fractions to deal with here, some thirds and some halves, but we should be okay. So 2 times 2, that's 4, minus 8 thirds plus 4 halves, minus negative 2. That's now going to be positive 1/3 and positive 1/2. So we keep going. We have 4 minus 8 thirds plus 4 halves. Distribute that negative, so plus 2 minus 1/3 minus 1/2. So if we put the like terms together, we get 6 minus 9 thirds plus 3 halves. So that's 6 minus 3 plus 3 halves, which is 4.5 or 9 halves. Okay, so we're just going to verify that with the calculator now to make sure that that is the correct answer. So to plug this in, we're going to go and pull up our integral. Lower limit is -1, upper limit is 2. Then we're going to put it in exactly like I've written it out here with 2 parentheses to start. 2 minus x squared, close that parenthesis, minus, second parenthesis, negative x, close that, with respect to x. We end up with 9 halves. So this is a very manageable integral to do, and the algebra at the end was not too bad. So this one you could probably expect to be able to do or be asked to do by hand. With a calculator, it's very, very quick. It takes just a few seconds to type it in, and then we get our answer very straight forward. So if you've got the calculator, then use it to your advantage. Save some time doing these problems. If not, doing them by hand is not too terrible. So we've got an example over here where we have x squared minus 1 and x plus 1. So we do need to first of all figure out which function's on top, and then we need to figure out the intersection of these two functions. If you've got a calculator, that work should be very easy. If you don't, then you do need to solve these two as a quadratic by hand. Either way, though, you should get them intersecting at 2 points, and those will be your limits, and then just figure out which function is on top. So take a moment, pause the video, and work on this example. Okay, so hopefully you have this figured out. I'm going to go through it both ways just to kind of show you the difference between how quick it can be on the calculator and how not how long. It's not a very long problem for this one, but just how much time you could save by doing it on the calculator versus doing it by hand. So if we are looking at these two functions, x squared minus 1, I know that that is an upwards opening parabola, and x plus 1 is going to be a line like that. I know I don't have any axes, but that is the general shape of these two curves in relation to each other. So that means that the x plus 1 should be on top, and the x squared minus 1 should be on bottom. The next thing we need to do is find these 2 points of intersection, and where these two meet is where the two equations are equal to each other. So we want to go and set this up. From here, it is a quadratic, so we want to get everything to one side or the other. I'm going to get everything to the left to keep this x squared positive, so we're going to minus x minus 1. So we'll have x squared minus x minus 2. This does factor, which is nice. We will have x plus 1, x minus 2. Which gives us solutions of -1 and 2. That is coincidental. These are different functions than this. It's just coincidental that they have the same intersections. Not everything will have those same two intersections, obviously. It just works out this way for this problem. Okay, so now we've got everything we need to set this integral up. So the integral from -1 to 2. Our top function is x plus 1. Our bottom function is x squared minus 1. And we are doing this integral with respect to x, so dx. Like the previous problem, I am going to do a little bit of cleaning up in that integrand, just so we have everything with the correct signs and all that, and we can combine any like terms. So we should end up with this, but with the opposite sign. So x plus 1 minus x squared plus 1 dx, which is x minus x squared plus 2 dx. So the same thing we had there again with opposite signs. So now we're ready to take the antiderivative of this. So the antiderivative of x is x squared over 2. The antiderivative of x squared is x cubed over 3. And the antiderivative of 2 is 2x. So very similar to what we had in the previous problem. We're still going to have fractions. It's actually the exact same antiderivative. We got a positive 2x. Yes, this is actually the exact same antiderivative. So they're slightly different functions, but we get the exact same antiderivative, which means our answer should be 9 halves. I'm going to go out on a limb there and guess 9 halves. Okay, so let's verify this all in the calculator and see just how easy this would be to do. So the first thing we're going to do is graph both of these functions, just to verify that what I had there was correct. So x squared minus 1, we see the parabola going through -1, opening upwards, and then x plus 1 should be a sloped line intersecting at 1. There we go. So exactly like I've got it there. We can, from this, basically tell the intersections. You can use the graphing tools if you want to analyze the graph and to find the intersections. There's my cursor. Okay, so we have left bound. We scroll over, we see the intersections at 1, 0. -1, 0, excuse me. And we can do it that way if we want. Or we can go into the calculator and use the solve function and take x squared minus 1, set that equal to x plus 1, and solve that for x. So we get those two solutions. Okay, either way you want to do it, we get those two solutions very quickly to verify that we were correct in our solving of the quadratic. Now we are on to the integral from -1 to 2. My calculator froze. -1 to 2 of, I'm going to plug it in as we had it over here. The first quantity is x plus 1, because that was on top, minus x squared minus 1, because that was on bottom, dx. And again, we end up with 9 halves. So very coincidental that this was the exact same answer, the exact same antiderivative as the first one. They were different functions in a different relation, but we ended up with the same area. It was probably a sort of mirrored graph of what we had originally. So again, just a coincidence that it worked out like that, but that's the general process. All right, moving on, we've got a lot more going on here with this function. And before we do that, in case you don't have an Inspire or an Inspire emulator, there is a website right there that will do these definite integrals for you, and it's very straightforward, user-friendly. To type this stuff in, it'll come up with the boxes very similar to the Inspire, which will help you do this online. So for this next example here, we have a curve, this upper curve, this blue curve, which is written right there, square root of x. Then we have this lower curve, this yellow curve, which is x minus 2. And the difference with this problem versus the previous problem, we now have this third technically curve in here, y equals 0. So what they're going to say with a problem like this is it's bounded by the curves y equals root x, y equals x minus 2, and y equals 0. So they've given us a third curve. What that does is it actually changes the boundaries of this region as we move along. As we start, it's bounded on the top by the square root of x and bounded on the bottom by y equals 0. But once we get to this point here, the lower bounds changes to be the line x minus 2. The upper bounds doesn't change, but the lower bounds does. So we don't have the same lower function throughout. And what that does is it changes the formula for finding these two different regions. There's actually two separate areas, A and B, that are formed by the two different functions of y equals 0 on the bottom versus x minus 2 on the bottom. So in order to get this correct area, we have to take two separate integrals of these pairings of functions. So the first integral they have for area A, this orange area, is the integral from 0 to 2. The top function is always going to be the square root of x. The bottom function is 0. They don't write that minus 0 as trivial, but just to know where they're coming from there. And then the B area, the light blue, starts at 2. So the x value where it changes is 2. So this one starts at 2 and it ends at 4, which is the intersection of these two functions. And that is still the square root of x, which is the top function, minus the bottom function, which is x minus 2. So we will have two different areas to calculate, and to get the total, we will have to add those two areas together. So this is no different in terms of the work that needs to be done with the areas, antiderivatives, either doing them by hand or using the calculator to do them. The difference is recognizing that there are two separate regions that have different bounding curves on them, and we have to take this integral with that in mind and take two separate integrals to get the correct area. If we don't, what will end up happening is if we just use the bottom function as x minus 2, we'll have this extra piece down here that we really aren't looking for. So if they give us a third function, what that generally means is that we're going to have two separate areas and we're going to need to break it apart like this. So let's go ahead and do the math here. So we pull up our integral from 0 to 2 of the square root of x. I'm not going to put minus 0, square root of x dx. So we get 4 squared root of 2 over 3, and we'll just go ahead and get a decimal approximation for that. So that's 1.88, we'll call it 6. And then we'll do the second integral here from 2 to 4 of that same square root of x minus the bottom function, which is x minus 2. We get another square root answer, so let's get a decimal for that, which is 1.448. And what we're going to do to get the total area is add those two areas together. So 1.886 plus what we just had, so a total of 3.3337. So 3.334. So doing it that way does get us the area we just need to recognize and then add the two areas together. But there are some other tools that we can use to get this area without doing two separate pieces. So if we continue down here, it starts to talk about integration with respect to y. So instead of integrating the function as an x function, we can actually flip our perspective and integrate it as y functions, x equals y functions. So we have the same basic formula here where we have f now of y minus g of y dy. So we're switching the variable from x to y. When we do this, instead of being top and bottom, now we're going to have right hand and left hand curves. So the right curve should be f, the left curve should be g. And if we look, the yellow curve each time is f, that's the curve farther to the right, and the blue curve each time is g, that's the curve farther to the left. So just like we did with x, if we are doing these problems with respect to y and they don't give us y coordinates, we can always find them by finding the y value now of the intersection, which is a little bit different. We just need to rewrite our equations in terms of y and then solve them for that variable. So if we look at this same problem that we just did, where we had the square root of x, y equals square root of x, and y equals x minus 2. Instead of doing that integral as two pieces and then adding them together, we can actually shift the perspective and take the integral with respect to y. In order to do that, though, we need to rearrange these functions as x equals y functions. And they've done that for us here. So if we have y equals the square root of x, to solve that for x, we're going to square both sides. So x is equal to y squared. And then if we have y equals x minus 2, to solve that for x, we just add 2 to both sides, and that gives us the x equals y plus 2. So now we've got this defined as functions of y. So we want to take a look at our intersection and the y value. So the y value here is 2. So that's going to be one of our limits. The other y value, we can basically figure these out by asking ourselves how high and how low does this function go. How high does this function go? The maximum y value is 2. How low does this function go? The minimum y value is y equals 0. So that is where we get our limits of integration from 0 to 2. And that's part of the reason why they showed us that very first slide with the substituting the limits of integration. We're not doing any use substitution in this problem, but we have resolve the equations for y, so we need to redo our limits in terms of y. Okay, so we have from 0 to 2. The right-hand function, they've done it very easy for us here. They've color-coded it still. So the right-hand function, the function on the right, is x equals y plus 2. So we're going to start as y plus 2. We're writing all of these as y functions. And then still subtract, and then the left-hand function is y squared, x equals y squared. We're taking all of this now with respect to y. We've shifted our perspective. Instead of doing an x integral, we're doing now a y integral. On your calculator, you don't actually have to change the variable. You can still do it as x as long as you have the equation written correctly. It doesn't actually matter what letter you use at all. So to prove that, instead of using y, I'm just going to go ahead and use t. So we'll have t plus 2 minus t squared dt. Calculator does not care what letter you use. And we get that, 10/3. Okay. So if we look back at this answer here, we had 3.334, which was an approximation here. If we actually were a little bit more careful with that, and this is my mistake, if we had the exact answer, it was 4 radical 2 over 3. And the exact answer for this one was 10/3 minus 4 radical 2 over 3. So if we would put those together, 10/3 minus 4 radical 2 over 3 plus 4 radical 2 over 3, these would cancel out and we would get the 3.3 repeating, or 10/3. And our calculator yelled at us right here. It gave us that exclamation point on this line saying, hey, this is an approximate answer, be careful, and I didn't pay attention to it, so that's on me. But our exact answer for that was 10/3, and then we do this integral with respect to y, and we see the same answer of 10/3. So which way should you use, which way is easier, which way is better to work with? There really isn't a great answer for that. If you understand that there are multiple pieces happening and you break it correctly and you do 2 separate integrals and add them together, if that works for you, great. That is, it's not going to take you much more time than rearranging both functions as x equals y equations, refinding those intersection points as the y coordinates, and then setting up that single integral with respect to y. It's usually about a wash. If they give the function to you in sort of a standard form, then you're solving it one way or the other. I would suggest trying to keep it into one integral instead of two separate integrals to add. But that's only if they give you, like, say, they might give you x minus y squared equals 0. Give it to you more of in a standard form problem. And then that's basically saying, hey, you decide what letter you want to take this integral in. If they've got it, though, as like y equals x squared or y equals square root of x, whatever, they're most likely hinting at that they want you to take the derivative with respect to x. But you always have the choice doing these to rearrange it the other way. It's not always easier. It's not always faster, but it is always an option. And they should give you the same answer no matter if you do it with two separate integrals and you add them together, or if you take one integral with the opposite letter. You should always get the exact same answer. If you don't, then you've done something wrong, and there's a lot of places that it can go wrong, so you have to kind of go back and dig through and see where you messed up. The rest of this talks about piecewise continuous functions, and then this example using Leibniz rule. We're not going to go through any of that. I'm just kind of stopping here at the rewriting of the integral and taking it with respect to y. So the major takeaways from this are area of a curve, take the top curve minus the bottom curve, evaluate it from the values they give you or the intersection of those two curves. If you need to split it up into two pieces, do that, add the two pieces together. That's going to occur when you've got three functions or more that are kind of limiting where you have the area. And you can always redo that sort of three equation piece as y equations and integrate with respect to y, and it should give you the same answer.